or less under USGS sort of guidance and resources. They're doing a huge amount for the community, and in particular, we like this model coast because of the sediment transport aspects that Chris has been involved in generating and now implementing into the numerical code. He is involved in a variety of different research venues. I'm going to let him sort of describe what those might be and picking whatever he decided to talk about today. So thank you.
Thanks, Tom. It's great to be here. And
one other thing I want to point out, he has an adjunct appointment or an affiliate appointment in ocean engineering. And so he serves on committees, and he's even participated in teaching courses here in the past. So,
which I'd love to do again. So, so one other aspect of my career, when I was doing my PhD, I was working in continental shelf depths, 90, 100 meters. And as time has gone on, the water's gotten shallower and shallower. I worked at MDCO, Martha's Vineyard Coastal Observatory. It was 10 or 15 meters deep. And now I've kind of emerged. So I'm subaerial now. And so this video that's been looping through was taken 2 winters ago. So one of the first times that we've used a drone, Peter Tchaikovsky, who's a colleague of mine at Woods Hole, took this video. And this was about the biggest change. This scarp went back. Do I have a page pointer? This, you can see that these stairs that used to go down to the beach like that, and this dune scarp went back about 8 meters during the storm. And the dune was kind of continuous through. There were some low points, but the storm totally broke over the dune and washed all this material, and this big lobe of sediment that you see here got moved into this tidal creek and actually blocked the tidal creek so that it didn't flow anymore. But this is just the oblique image. Looks great, it's fun to look at, and you can learn a lot by looking at it. But the other thing that we did the same very cold day was we made a map using the drone, and that's basically what I'm going to talk about today. Who here has heard of structure from motion? That's kind of a lingo thing. Okay, so everybody. So I may be telling you more than or less than you already know. This is what the map that Peter Tchaikovsky made after that lobe of sediment that you were looking at is right here. This is where the dune retreated, and this is the post-storm model. There wasn't a good pre-storm model. The last time LiDAR was flown was here. This is the tidal creek that got blocked, and this is a little overwash channel. And there's another one over here that you'll see later on. And then the great thing about that is you can do a difference map. So this is kind of a crude difference map between the LiDAR and as the before map and the structure from motion map from the drone afterwards. But you can see the dune. This is the ocean side. This dune lost all of this material here and washed over. And this part here, where it completely broached the dune, had a kind of a dune crest. And so this is the ocean side. I flipped this around just to keep you on your toes. This is the ocean side here. Had a pretty high dune crest, and this is the tidal channel, and that all got smoothed out. And this little lobe of sediment that you see here on top of the marsh. So that's kind of a dramatic picture. I'm gonna go through and talk about a little bit about the background of structure for motion as we use it in drones. And the more formal name for structure for motion is multiview photogrammetry. And I've been doing it now for about 2 years, using Sandwich Beach a lot as kind of our test ground. And a lot of people have helped me out. Peter Tchaikovsky has done most of the flying of the drones. There's another company that worked for us that I'll mention, which is AirShark, and they actually have an office in Portsmouth, so they're kind of a local company if anybody needs a collaborator. And then a lot of people work in the field when we do this, so I wanted to put their names up. My credentials in this field are pretty slim. As I said, I'm a sediment transport person, but I've now mapped Town Neck Beach at least 10 times, sometimes multiple times on the same day. We're the first team to fly in a national park, so we got permit that the permitting was the hard part, not the flying. We're using Agisoft Photoscan, and there's a guy who used to work for the BLM who's kind of a wizard at it, and he's kind of a guru, and we've learned a lot of things. There's a lot more than you might know about how to use Photoscan. I'll try and impart some of that. And now we've got a project called Remote Sensing of Coastal Change at the USGS, where we're using all kinds of photogrammetric and techniques to map coastal change on a lot of scales. So the main difference between stereo photogrammetry, the old school thing where you had the stereo viewers and you were measuring things and finding points on the 2 different images, is that you have multiple viewpoints. You have more than two cameras, and in some cases you may have 1,000 viewpoints. So at the first cut, you've got a lot of viewpoints of something that's not really moving. And the other thing is that it used to be that you had to precisely navigate your camera. You had to know exactly where your camera was and where the second camera was to do the geometry to figure out where the points are. This relaxes that requirement. In fact, in the software we use, you don't even have to know anything about the camera. You can literally, you guys can do this tonight before you go get a beer. You can take 10 pictures of something with your phone, stick it in this software, and you'll have a 3D model 20 minutes later. So that it's gotten to that point. But if you want to do photogrammetry and you want to measure things, you have to pin it down somehow. One way to pin it down is to know exactly where the camera is and where you're looking and what the geometry is. Turns out if you have a camera with a camera plane like this and it's looking over there, just the tiniest little bit of camera movement, just a slight angle, is going to have a big arc on the ground. If you invert it and you flip it around and use things in the scene to lock down the camera, you get a lot more control. So we use ground control points, and if there was one thing we could do to advance this technology to the next point, it would be somehow make that easier, because you're going to see that that's where all the effort comes in. And you get a point cloud, which is very much like the first product that you get from LiDAR. You get a bunch of registered X, Y, Z location points. With photogrammetry, they also have color, so that really helps you interpret the points and understand them. In contrast to LiDAR, sometimes LiDAR might have backscatter intensity, or it may even have spectral information, but it doesn't have that beautiful picture that you get out of this. And the software really is pretty amazing. I do a lot of modeling. I've done lots of things with software. I don't think I've ever encountered any software that has to do as many different things as PhotoScan does in order to get a final product. And it's kind of magic, because it has to do these things. First of all, it has to just imagine a digital picture. It has to find potential key points. It has to find things that it's going to match in other pictures. And the things that it finds, you and I can find things. You can say, oh, there's a corner of a house, or there's a big rock on the beach, or there's some. But the software has to find these things, and based only on pixels. Then it has to find those same things in adjacent images that are overlapping with overlapping information. And then it has to reconstruct the geometry, saying, well, I've got these 5 points in this image and they match these 5 points in this image. And so where was the camera that saw those, and reconstruct that geometry, which it can do kind of analytically for 2 or 3 images. But once you get to 1,000 images, it becomes an iterative thing that has to kind of keep adjusting. And then some of the points are bogus, right? Because it's only software. And so some of the points that it found were wrong. And it has to go through that. There's also the lens calibration. And to be honest, traditional photogrammetry people kind of get uptight about that. They say, we spend a lot of time calibrating our lens. We want to have a really perfect lens calibration. But when you think about this problem, you've got 1,000 cameras, which each have 6 parameters, because you need to know their XY position and then their orientation. And then you've got all these, maybe up to 1,000 tie points between 1,000 images. That's all your unknowns that you're trying to tie together. 12 camera lens calibrations is kind of peanuts to add to that. And so most structure for motion people solve the camera calibration using the data that they got from all these images. Then after you do that, and you've got the tie points and you've got the geometry all straightened out, then you have to somehow add the whole color from the images. You've only taken a subsampling of a few points, maybe 1,000 points per image out of a 16 megapixel image. Then you have to add all those other 16 megapixels back in and put some kind of onto the geometry. So there's kind of an interpolation problem of filling in the gaps. And then you can finally either generate a map or a kind of a 2D, either a 2D product or a 3D product, and put that signal on there. So software does a lot of things. You guys probably know this. Up until a couple of years ago, the LiDAR was basically the gold standard for subaerial mapping. And it's always checked out with ground GPS, which is somebody walking around with a good GPS. Our GPS systems now, we're pretty confident that we can go back to hard points with approximately multi-millimeter accuracy. So any day we can go and measure a particular point within a few millimeters, given a good RTK system. And LiDARs, of course, can give you that kind of thing. But now structure for motion involves having something up in the air, a balloon, a drone, a camera on a stick, looking at the scene. And the key is to plan your data collection so you get a lot of overlap. We'd like to get at least 6 images, 6 views of every point on the image. So the workflow, this is me going out on a tidal flat with my point and shoot camera. I took about 20 pictures with this crummy camera. This is the first time I did this, so this all is a couple of hours. When you put it in the software, you get it reconstructs where it thinks all the cameras where I walked around this tidal flat, and then I went down, and then I held my camera up. And so these are all the camera planes with the little pointers pointing at the scene, and this is the sparse point cloud that it came in. And then I had these targets that I had kind of roughly measured where they were, and I picked them out. And then you go to dense point cloud and you add the texture that you get out of that. And all this happens in one set of software. I could be happy to talk about other software, but the one important thing is this is all kind of scaled by the pixels in the camera. So you can get microscopic measurements and look at things in very tight detail, or you can do this with satellite imagery and everything in between. It's all a function of how big a pixel is on the ground. And you can do it with things that are not just maps. So I've got some models that I made. I put them on Sketchfab so people can look at them. This is the kind of thing I'm going to be talking about, is kind of planar models of beaches. But this is one of our tripods that we put, our quad pod that we put on the bottom, and you can make a dimensionally correct 3D model of this. Kind of helps to remember how high was that ADV that we put in there. Stuff like this is a shipwreck down in Florida where the water's clear, just taken from completely non-navigated underwater pictures. This is my daughter's art project. This is a scarp on the Sandwich Beach. So these are all the kinds of things you can build with software. And just to keep drilling on this point, this is Ian Ray from Air Shark in Portsmouth, and they have a very nice camera that they can fly on this drone, and these guys do a good job. So I recommend them. This is me with my drone, because I'm a federal employee, so I'm not allowed to fly drones yet. We now have 2 officially registered drone pilots, so I do this on a stick. This is in this Overwatch channel that I like to look at. You can do it from these kind of platforms, have a couple of stereo cameras and drive along the beaches and look up at the cliffs. You can do it with underwater photography. Here's some ripples that have been mapped with actually pretty crappy pictures, right? So even these pictures can generate some fairly nice images of the ripples. Here's an example where we tried to do it through the water. This is a little estuary off Buzzards Bay. It's pretty shallow. A lot of this dark stuff is seagrass that is growing, and the black areas are places where we didn't get through the water. But down here, well, I'll show you the map with me.
How high is the drone flying, like, for instance, in that image you just showed us?
So in that last image, I think we ended up with 50 meters. We experimented quite a bit on the vertical, but it depends on how much detail you want, because the closer you get, the smaller your footprint is on the ground, and the more detail you get per pixel. But I think that was about 50 meters.
So the parts where you don't see in the water, it's finding that and not finding a solution and telling you, I can't do anything about that.
So
are you filtering the data in some other way?
No, this is a place where it couldn't come up with the answer.
And it told you it couldn't. So.
The reason it can't come up with an answer here is because, well, first of all, there's a little bit of waves, right? So this doesn't work. You can't go through water if there's any waves. Well, I can't. There's a guy out at NASA Ames who can, but he's smarter than me. So fluid lensing, look up Bed's fluid lensing. He actually uses the waves to focus the light, but it takes him a supercomputer, weeks to map one thing. So with refraction, you would think this can't work because the light's coming in like this. It's refracting in the water, so it's not actually looking at the spot that you think it's looking at. But you're getting 6 different views. So, and you're also 50 meters looking through 2 meters. So there's not that big a translocation, and you're averaging all the points. And in the end, in this little estuary, in the spring before any phytoplankton bloom, all this kind of rough, bumpy stuff is where the seagrass is, and the bottom is rough. Some of these smooth sand beds show up more cleanly, and here it couldn't find a spot that it would recognize in the bottom.
Is it using video imaging, or is it...
Still pictures work better. There's a lot more a lot more detail in still pictures. So in the end, the way we program the drone is to fly along and click, and we're shooting to have each image overlap by about 60% from the, so there's a lot of duplication along track line and about 50% across track on the parallel track.
How rapidly is it taking pictures?
It ends up being 1 to 2 seconds. It depends on how fast you're flying and how high you're flying. And there's software that allows you to plan all that. So you say, well, I want a pixel to be a centimeter on the ground, so that means you have to be this high, and that means if you want 60% overlap, that you have to go this far, and if you're going to fly at 10 meters a second, and the software will help you figure all that out. So you can.
How big an image is it? Is it 10 megabit camera, or is it?
Well, you can do this with whatever camera you have. So in practical terms, the DJI Phantom cameras are pretty good. They only have one perverse thing, which is a rolling shutter. Anybody know what a rolling shutter is? You do. So what a rolling shutter is like a regular digital camera will open the aperture and the whole CCD will be exposed at the same time. With a rolling shutter, you're moving the light across the shutter as a function of time. And so this end of the CCD is not synchronous with this end of the CCD, which is a problem if your drone is not in the same place by the time it gets there, right? So rolling shutters are not as good, but they're still okay. They just kind of add some blur to it. And if you can afford a really good camera and you've got something that will keep it up in the air, good cameras tend to be heavier, so you need a bigger drone, and that takes more battery. It doesn't fly as long. There's trade-offs there. So this is just our attempt to map seagrass by looking at the roughness. Here's a profile through this section. This is sand, and then it gets kind of bumpy in the seagrass. And seagrass is 50 centimeters, the canopy is 50 centimeters high. And it worked pretty well. So we're going to try that again this year. We're going to use, we're actually going to survey it and quantify just how good it works. And of course, it could work way better in the Bahamas or someplace. So, but here's our problem. So this is Sandwich Beach, and you're going to see more of this now. But the point of this picture, the black dots are places where we put ground control targets. We often use these, and I'll discuss. We've gone around and around about what to use. This is about a 4 foot by 4 foot target, just a black and white diamond. It's plastic, and we spread it out and we hold it down with a pile of sand or rocks if we're in a cobbly place, or tent pegs if we're in a marshy place. And in this particular case, they were distributed like this. This isn't necessarily, we don't need that many. But what you're seeing contoured here that is getting up to 50 centimeters and down to 50 centimeters on the edges here is the difference between two maps that we made on the same day with the same control, but they were with different drones and different cameras. And so, and one camera was higher resolution, and so it was kind of two independent maps using the same ground control. And what you see is that within the white area is plus or minus 5 centimeters. So for all intents and purposes, we can't recognize the difference between plus or minus 5 centimeters. And you see we're good all through this area where we're inside the clouded control points. As soon as you get outside of the control points, they start diverging and going off in different directions. And one might be right and the other wrong, or they might both be wrong. But you start seeing that kind of difference. And this is the biggest problem that we have now. I'm not going to give you a solution, but if we could reduce the number of ground control points or make them easier, that'd be a good thing. My favorite plan is to have 30 drones all fly out and land, and those will be our ground control points, and then we'll just whistle and they'll all come back and we'll be done, and we won't have to walk around in the marsh and take little boats and put up the cameras. So there's some things you can do to minimize that kind of distortion. You can have a good lens. I'm sorry. Here's where that error comes from, and then the red is things that you can do. But you can have lenses. All cameras have some lens distortion. The camera location, the camera look angle, and incorrect high point matches. All that's kind of a geometry problem, and by taking pictures with the optimal geometry, you can minimize that. Ambiguous tie points are things that it finds in the images that aren't really tie points. They're different things that it found. Again, high quality images. This turns out to be a real photographer's problem. You start off with kind of a mapping mentality, and then you realize beginning, it's really all about the photographs. And then the ground control points, we accumulate a huge knowledge of what works and what doesn't work for things to look at on the ground. And then how you do this, there are about probably 3 or 4 mainstream commercial products and then a whole host of open source products and not so mainstream products for doing the software. And that's a very rapidly evolving field that if I tell you something today, you'll find out that that's not the case by next week. So, but I'm happy to talk to somebody. Here's an example though of when we do it right, when we get our control points out, this is again sandwich, and now this is kind of just a shaded relief map of the beach. Now, I'll tell you what this part that looks like a concrete bunker is later, but it's a nourished dune. And then we've got some points here, points along here at the base and the top of the dune, points kind of cross short profiles, and all those are independent RTK points, 836 of them that are probably good realistically within a centimeter or two. You know, I mean, you're putting a stake on sand, and you have a bubble, but you know the antenna can move a little. So say a couple of centimeters for all those RTK points. And what I'm comparing them with is the digital elevation model that we've extracted from the images. So this digital elevation model that you're seeing shaded here is 10 centimeters. We just take the closest point from the RTK and we compare it. And that's the histogram of how different the RTK points are from our final product. And so plus or minus 50 centimeters is the scale here. And the mean difference is only about 4 millimeters. And the RMS difference is 8.7 centimeters, which is actually one of our worst ones. Here's another one. Same place, a little more marsh got covered down here. And here now the mean difference is 1.3 centimeters, but the RMS difference is only 4 centimeters. So
that's just for the area where you have the control points.
No. These are all completely independent. These are not the control points. The control points are out here. They're not shown in this picture. But they had a
both in the marsh and on the beach.
The control, we're not comparing in the marsh. Here's where we're comparing. All these little black dots that are a little hard to see. The marsh is hard. We're not mapping the marsh, first of all, so there's not much emphasis in that, but that's the next thing that we're trying to turn our attention to is how to do this in the marsh. So the bottom line, if people were to ask me to summarize, I would say that our maps, now that we know what we're doing in Sandwich, we're making maps that are accurate to order of a centimeter and precise to order 5 to 10 centimeters. So what are we trying to do with these things? The long-term goals are basically to be able, we'd like to be able to forecast when somebody says there's a nor'easter like tonight, we'd like to be able to say, you know, that might erode the dune by 1 meter or 2 meters, or no, you're not going to have to worry about it, or it's going to cause overwash. The other thing you'll see over the course of this talk is that this nourished berm that they use, they dredge material from the Cape Cod Canal and they put it on this beach to protect it. It's going away pretty quickly. Could they have put it in at a different slope or in a different place? How can they nourish that beach and make it last a little longer? In the meantime, we've spent most of our effort learning how to do this right. And we're documenting changes in the beach and the overwash. And then finally, we've got the first step in getting the models right is getting a good before and after situation to compare them with. And the 2013 LiDAR is not adequate before. The whole time scale is like tonight and tomorrow. And this kind of demonstrates that. So this is a house that is on the same beach. We're now looking from offshore on. This is one of the many little crummy rock groins that's on the beach. There's a long story about why this has been nourished by the town, and the town has paid for it. All this planted dune grass is all nice and lined up. This is a scarp on the edge of this nourished dune that wasn't there to begin with. These are, they had a little fence to keep people from walking on the dune. It's now all tangled up and tied. This is after a storm this year, right before Valentine's Day. The private neighbors did not sign on to the federal project. The Corps of Engineers required that they get access to the beach and in perpetuity, that they allow public access to the beach if they were going to put the sand on the beach. And this guy said no, And this guy actually, I don't know what his response was, but I think he'd already paid for this, all these coconut husk filled bags here. So this was the end of the project. So this sweet elderly couple, they're both in their 80s, and they had never heard of coastal erosion when they bought that house 20 years ago. It just wasn't on their map. And this was the line before the nourishment, like literally 5 feet from the edge of their house was a 10-foot scarp. And now they're watching this erode kind of, you know, they're a little nervous. And that little white spot there is a beach cam that you guys can go to and look. If you Google Sandwich Beach Cam, you can watch this all as it has played out over the last year. So here's what we're doing. We've got the beach cam on this house. The camera there was looking there, looking back. So you see that little dent here, and these are all the private properties that are nourishing their own beach. Beach cam is here, and it's kind of looking off this way. This thing that looks like a concrete bunker is the nourished material that was as it was put in. This was the part that got blown out in that 2015 storm. You can see the remnants of the sand over on the marsh here. The channel was dug out. This is my favorite little erosion overwash channel that I've been looking at, and we've had pressure sensors on either side, and I'll show you some results. Last year we got a wave rider buoy right about here, right plunk in the middle of Cape Cod Bay, so we now have some offshore data. We've also got about here all winter long we've had an underwater ADCP with measuring waves and currents and water levels and turbidity. So we're kind of building up an infrastructure so that we can respond to these storms and look at them. And this is
just, go back that last slide for a second.
Yeah.
What's that kind of bright yellow area directly below the overwash?
This?
To the right.
Yeah.
Right there. What's that?
Okay, well, there's a tidal channel here. This is a dropout in the map, so it's a hole through to the background yellow. So that's not really anything. This is an orthophoto overlaid on, I think this is the old LiDAR, and maybe the LiDAR didn't get all the way through here, so there's a hole in the LiDAR map. Or it might be one of the other, it's the LiDAR, I can tell from over here. So, so this is just a bad plotting on my part, I guess. So we've made a number of maps. The 2015 was our first one. Last year we made 4 maps last winter, and this year we've made 5 maps. So you can't see too many differences in these. The biggest differences are right here at this northwest edge of the nourishment, where if you compare, here it is nice and fresh, it had a nice sharp corner to it, but by the time you get down to here, it got moved. And at one point, after this storm, but before this, they went out with bulldozers and they reduced it. They had basically a 9-foot scarp on this corner here, and they didn't want to start the summer like that, so they smoothed it out. They had initially put the nourishment in it at a 1 in 20 slope because they didn't have as much sand as they thought they were going to get from the canal. And then they reduced it to they started at 1 in 10. They changed it to a 1 in 20 slope with bulldozers. And so sometimes the changes that we're mapping are not natural. And one of the advantages of this rapid response thing is that they do go out and they put bulldozers on and they dredge stuff out of the canal. And so if you don't go out and map pretty quickly, if you wait for the next LiDAR flight that NOAA and the Corps of Engineers schedules, you're not measuring the real changes that the storm wrought. You're measuring something else. So here's that same spot we've been kind of focusing on. Here's the house. There's a little white spot that's our camera. You can see a few of our targets in this image. You can see a few of us in the image. And I think what I'm going to do is I'm going to peel back. So this is going to loop through, and what you're seeing is basically what it looked like right as they put in the initial groin. So all this is the nourished thing, and this is what it looks like actually the last time we mapped it. So so this was about a couple weeks ago. So a couple things happened. They planted the dune grass on the top of the dune. The dune eroded back and formed this scarp, which is now about 9 feet high again. And I noticed the last time I looked at the beach cam yesterday, I saw a little survey stake. So they're probably going to go with the bulldozer and smooth it out again and regrade that. You can see cars have moved. They built a fence down here. They built this path here.
When they regraded, I mean, they just reducing the slope of the scarp, or are they pushing sand up from the beach? Or?
No, they don't go down to the beach and they take the sand from the project and they move it down. So the top, the flat part of the dune on the top is going to get cut away again when they do it again. So this is the same thing, but now looking at the digital elevation model. And so these are two of the models from the drone flights, and you can kind of see, stuff that's not supposed to change doesn't change, like the house hasn't moved. Cars moved. They had a little Jersey barrier here, and cars were here, and then they left. You can actually see the dune grass grow in this because they planted it not long after this first one was taken. It grew all summer long, and it's now fairly high.
What's going on in the overwash on the left side?
Which one?
By the arrow. It was a big change in elevation.
Okay, so that's vegetation, and some of it is trees actually growing a little bit, and some of it is the fact that the trees look very different depending on what the lighting is like. And so we're not paying too much attention right now to how to map big vegetation. We're starting to think seriously about how to map marsh-sized vegetation. Vegetation is handled, most of you probably know this, in LiDAR. Basically, they figured that the farthest point is looking through the vegetation and might have found the ground. And so they use geometry. Not as many points from structure from motion get through. We don't get as many points as you would with a LiDAR cloud. So that doesn't work quite as well because not as many get through. But we also have color. So green might be leaves and brown might be ground. There's ways to start teasing that out.
Chris?
Yeah?
Does the change in roughness in the water real?
No. So water doesn't work until the end of the talk. So we can make difference maps. And now again, the areas that are kind of white or gray are places that are plus or minus, and we've been pretty strict here, plus or minus 5 centimeters, we're saying is no change. And then and places that are red are places that are now higher than they were, and places that are blue are now lower. So we can quantify these changes fairly precisely. There's a couple other artifacts here. In addition to the cars that have appeared and disappeared here, this stripe is the shadow of a telephone pole. Okay, so the shadow doesn't actually make it high or low, but what makes it high or low is the shadow is moving over the course of the time that we're mapping. And so that's an artifact. So is this shadow from the fence. And there's probably other shadows that are other artifacts. But we also can learn a lot that's quantified from this. And we can look at a bigger picture of the whole beach. And unfortunately, the other problem with this, of course, is it's all subaerial. And we always map at low tide, but sometimes the tide's lower than that. We've got about a 12-foot tide range here, so there's about a 4-meter tidal range. Sometimes we get out pretty far, and other times we don't. This outer line is roughly the mean low water line. And this particular map lets us look out a lot farther, but these numbers don't always capture that. So this is the change from the time they regraded it last year to about 2 weeks ago, which was the last time we mapped it. And so we gained a little bit net here. The red is gain, the blue is loss. We lost a bunch in the front of the nourished dune, and most of that was erosion of the dune face. We lost a bunch here. We gained a whole bunch in this section. We gained quite a bit here. In this particular one, we lost some in this little overwash fan, and overall we lost, the net change was about 2,500 cubic meters for, well, let me just show you the next slide, which is, these are what the changes were like just in the month after they first built it. So January 22nd was the day that they signed off and said the project is done, and we happened to map it that day. Then there were 2 nor'easters last year, and we mapped it again in February. Big losses here, big losses here, big losses here, although you can see we didn't capture all this gain here. A little bit of gain here, big losses down at this end, a little bit of gain here, including my little favorite spot, the deposition on this overwash fan that got moved back. And so they put 100,000 cubic meters of material on the nourished berm, and they lost 21,000, at least within the area that we surveyed here, in a month. And we're down over the following year after they regraded it, we only lost about 10% of this. So as you can imagine, exponential changes in the beginning and then kind of.
Where does it go, do you know?
Well,
Does it go offshore? And
okay, so
that's what's lost?
well, some of it goes downdrift, and this is a fairly small inlet that I think gets bypassed. Some of it goes downdrift. I think there's a lot of exchange on and off because I'm glossing over the in-between maps. There's quite a bit of variation, and you'll see it gain and lose. So there's material moving onshore and offshore here. And you see we're not capturing all the changes either here. So this big loss here, quite a bit is on the lower beach face now, where there's some accumulation.
Chris, if there had been no nourishment, would you see net accretion across the entire?
No, I don't think so. I think we would have seen net loss, net erosion. We might, or maybe we would have seen loss right here at the dune bluff and some of that ending up on the beach. The bigger problem is that right about here is where the Cape Cod Canal is, and the source of all the sediment is up here in Plymouth where there are these big bluffs that are eroding. And this is kind of the net drift is along in this direction. And so the sediment supply has been cut off by the jetties for the Cape Cod Canal. And so regionally, over the last 100 years, this area has been starved.
Before you leave that, I'm sorry.
Sorry, go ahead.
So you're not mapping outside of the black lines, but it does show
Well,
accretion on the lower beach.
no, I'm not, these numbers are within the black boxes. Yeah, we're seeing some changes. The coverage varies. In this case, the coverage includes all the areas that are colored, but the numbers only come from inside the boxes. So I'm not in this, I could quantify everything that's colored if I wanted to, but I wanted to compare apples to apples, so I drew some boxes. So I could go out a little farther in this.
Why wouldn't you? Because if it's moving from the bluff, from the dunes to the lower beach, it's not lost from the system.
You're right. But then I'm still not closing the system probably because there's changes farther offshore. So I think I've talked to some of you guys about my autonomous jet kayak, and we map that. We use that to map at high tide offshore, and we're going to do that again. But you know, so the cool thing about the drone is you go out there and literally these maps require, if we map it double, it takes 45 minutes of flying. So we map the entire area in two completely different flight patterns. And so whereas the jet yak is a whole multi-day thing to launch it, and you got to babysit it, and it goes back and forth. And
Is that flight time doesn't include the time it takes to put out your ground control plan?
No. And so our current thing now is when we decide we're going to map, like we might on Monday, we call the weather department and we schedule low tide to be at noon, and we make it sunny all day but no wind, and and warm preferably, and so the guys can get the targets out in about we send kind of two teams. One goes around this way, and another team goes around up here. We have targets starting up here. Takes about an hour and a half to get the targets out, and at that point we can fly. You have all day, or at least until high tide, to measure where the targets are, but you got to get them out first, and then we got to collect it. So the whole thing takes our field crew on the beach about 3 hours, and that's about typically 6 people for the survey crew, and then Peter to fly the drone. So. And then the other things that we're doing, so that was mostly about the mapping. This is the little overwash channel. This is kind of the entrance. Here's the beach. Last year we put a pressure sensor on the end of the groin, which is probably not the best place to measure waves, but it was about as far out as we could get. This year we've got the offshore thing measuring it. And we put these tilt sensors, which didn't work very well because the water wasn't deep enough, but we also had pressure sensors. We put one kind of at the entrance to the overwash channel and one kind of back on the delta where the overwash channel came into the back barrier. And so here's what a wave looks like coming down the beach. This is the measurements at the groin, so that's where we're surveying it in here. And the reason that yellow bar is so big is because it's got the incident wave energy. We're measuring at 4 hertz, so it's got the incident waves on top of the tides. And so here's the tide, and then here's the waves, and that gives a big spread. And this purple one is on the back side, so that's just kind of the tide in the marsh. and then the red and the blue, the red's back here and the blue's up here. And so just barely at high tide on this one, a few waves started hitting the blue sensor. On this next tide, waves hit the blue sensor and ran to the backside and hit the red sensor. You notice that the waves offshore were a little higher. You can picture that, and probably if you've taken Tom's course, waves are breaking and declining as they come in, but they're still running up the beach and getting to this point. And then they wash over like this, but by the time they get, so this sensor is right about here, and then this sensor is back a little bit. By the time they get there, it's open channel flow. It's modulated a little bit by infragravity frequencies with water depth, but it's just basically almost steady flow. It's not really, I kind of thought these waves would propagate all the way across the barrier, but they don't. They disappear. Actually, here's a time series. So this is the time series of those two sites, and you can take the time series of the water elevations, and you can make water slopes out of them, and if you've got a water slope and a water depth, you can estimate the shear stress and the velocities, and then you can whip out your sediment transport calculations and calculate, and the bottom line is this is the net transport over that one tidal cycle. And that, and as it turns out, if you integrate that, it came out really, I don't know if it's the next slide or not. Here, here's the little amount of sediment that deposited during that, and the integral of that sediment transport equation came out scarily close to the amount of material we measured here. So it's kind of an example of, and we're just starting to actually start using these maps now to make things like that, and to run models of what we expect the overwash to be. So here's overwash that's just barely overtopping, and the waves are coming over the backside and running down and then forming.
Is this X Beach?
This is swash. So swash is a Boussinesque-like wave-by-wave modeling system, and it's only it's got multiple depths. I think there are 15 water depths in here, but it models individual waves. And I can talk more about swash to somebody, but this is the same model setup, but with the elevation, the water depth higher. So we can compare how much transport would happen as the tide changes and the water changes over the course of the storm.
Does swash do the sediment transport as well?
No. No, I kind of, well, it does do, it has a sediment transport component in it, but what I'm interested in about swash is that it provides the wave asymmetry. So each wave is skewed forward, and so you can do the bed load transport, including the wave asymmetry. And there's another thing that I think is kind of interesting. We got off on another topic. In these two cases, the flux of water is actually not constrained. It doesn't just pile up against the shore. So normally, if you've got a beach and the water is setting up against the shore, that's what generates the undertow, right? Because there's got to be a return flow. You're forcing water against the shore. It's piling up, and that causes a return flow somewhere. But if you let water flow over the top of the barrier or under the backside, you don't constrain that anymore, and the elevations change, and that allows the net flow to be kind of more positive along the beach face. So it's not really the topic of this talk, but it's something I thought I'd show. I have two more parts to this talk. I'm going to fly through this part really quickly. It's I'm probably just about done anyway, but let me show you one more application of structure for motion, since this is the topic. And now we're talking about 4D structure for motion. So the thing about 4D is one more dimension, right? And that's, of course, time. And it turns out that if you combine photos from two different times, you can help align the geometry. In this case, that's what we're doing. So we've got more images of more or less the same thing. Some stuff has changed, some hasn't. And we tried this out last year. Hurricane Matthew came up the coast, kind of meandered around and gave all the weather forecasters great anxiety for a long time. And right afterwards, NOAA flew oblique photos like this. So this is in the east coast of Florida, and these are overwash slopes. This beach eroded back, caused the overwash around these houses. And this is an example of a kind of a zoomed-in version of one of the oblique photos that NOAA flew about 4 days after the storm. Here's the storm track coming up the coast. St. Augustine Beach is a little bit north of where we were this place I'm talking about is right about here in Florida, just a little bit south of St. Augustine. And so here's the theory. There's pictures from one year, there's pictures from another year. Putting all those pictures together helps constrain the geometry of where the cameras had to be. These pictures were kind of roughly navigated. We kind of knew where they were with one GPS fix per picture, basically, and no idea about what the angle was. And we picked a bunch of control points using really old LiDARs, it turned out. The last LiDAR data that we had available was 2010. So we looked at roads and flat places and the tops of houses and used that as control points, basically all desktop control, nobody actually on the beach. And this is how you do it, photo scan. So here's a 2015 set of pictures that Noah took. We were comparing the 2015 with the 2016. And here's after Hurricane Matthew. And then here is the change that we measured between those. So erosion on the beach, and in blue is deposition, accretion. The colors flipped from the last ones. So erosion now is red and deposition is blue. Here's another before, a little farther to the north along the coast. And again, the beach is here, the houses are here. Afterwards, the beach is eroded, all these overwash fans by the houses. And then here's the deposition map showing the overwash. If you looked carefully in this picture, there's already a bulldozer moving sand on this, and this was 4 days after the storm. Bigger signal is here, a little farther north. This inlet formed during the storm. And so here's the changes, big erosion on the beach, a lot of deposition on these overwash fans. And so the reason that we thought this was a useful thing to do was because we got these way faster. The LiDAR flights ended up being a month later. So we did get LiDAR, post-Matthew LiDAR coverage, and we literally got it online about 3 weeks ago. So now we're comparing to see how good these estimates of the change were, and we're going to look at that. I'll show you one more. So we had a meeting about this last year, and there's one more way to do 4D structure for motion, and that is to measure something that's moving. Who's been to Santa Cruz? Anybody been to Santa Cruz? This is one of the best surf spots in the U.S. for people to watch surfing, because you can just stand there on this bluff, and these waves just curl around this point break here. There's a surfer right there, but there's the same surfer. So these are all synchronous pictures taken at the exact same time. We set it up on the bluff of these cameras, and they have a little radio, and they talk to each other, and they all click at exactly the same time. And there's me pointing the clicker. And so here's a point cloud reconstructed from the motion. And these point clouds we were shooting at about 1 second, but I think these are 2 seconds apart. So you can see the wave propagating in. There's some holes in the point cloud because we couldn't see on the back side of the wave. But by looking at the wave from 3 different angles all at the same time, we can make a 3D reconstruction of the water surface.
Do you need 3? Can you do it with 2?
You can do it with 2. It would be better if you had 5, and it'd be better if they were higher. So there's a way now to synchronize cameras using the GPS signal, and you have to have them very synchronous, but you can take part of the GPS signal. So you could have 3 drones all flying and take pictures simultaneously of the water surface, which is huge, right, for all of us, because you've got these pictures. You can measure the wave height, you can measure the wave angle, you can measure the wave speed because you've got time, you can measure the amount of braking.
But you have no control for how does it get a elevation?
So you can get local control, but in this case we had control on the cliffs. So here's the point cloud. This is a wireframe reconstruction, and then this is going to be my Three Stooges animation. Ready? And actually, I'll show you the surfer. He's not very well resolved in the point cloud. These are the points. So these are X, Y, Z points. A couple million of them in this picture of points that are located in space and also have color. It was kind of a crummy day, and the surfer is right in here somewhere.
So even though the cameras are fixed in position, you don't need to tell the software where it is.
Right.
Can you tell it?
Yes.
Constrain it?
Yeah, you can constrain it. And so this was literally what we did at lunchtime during a meeting, and just to explore the whether or not this is a place that we could go. And you can see it's got a lot of potential. So thank you very much. Any questions?
I was curious for this. Do you need to capture the area with all the cameras to get the XYZ data, or does only one data or one camera need to get it to sort of click in?
You need overlap among a couple of cameras, and then the reason to have more cameras is to have more angles on something that's three-dimensional like this. It'd be nice to have another camera looking at the back of the wave, but all the cameras need to overlap significantly with the next camera in the picture. And so the structure for motion is you move the camera around and take a picture of something that's fixed, but this approach is to have a lot of cameras taking simultaneous pictures of something that's moving.
So if you had the cameras on the list, like you did in the drone over top, would you be able to, would there be enough overlap with the mounted cameras in the drone?
Yeah, yeah. I mean, that's all mission planning, right? That's planning where the cameras are and where they're looking in.
So things that move in the image are not great, like you got a flock of birds or people walking, but those disappear if you have enough images of the same spot. Those points just get thrown out. Can't find a match.
They either get thrown out or they get turned into something nonsensical, like the surf zone when we map in Sandwich.
Yep.
It just turns into complete rubbish.
Do you have to go then afterwards and tell them that you don't like that, or does it come back with a flag that says, I'm not real confident about this, so you can set a tolerance to get rid of stuff?
You get, so one of the steps in photoscan, and if anybody's doing this, I actually have a lot of advice because we've worked on this, but there's a point, the key to getting a good reconstruction is building a sparse point cloud that you trust, right? So that was your question. Are these good points to bolt your framework onto? And there are a number of different metrics that allow you to say yes or no, and the surf zone typically fails those. So as you triage and you look for points to eliminate, the surf zone points, for the most part, end up disappearing. Now, some guys like to kind of mask those points out to start with, and if you're looking with oblique photography where you have like the surf zone in the front, what you're interested in here, and the horizon and the distance in the back, a lot of people will mask out those two before they look at this stuff in between. But what we've been doing is just playing it all. A lot of it tends to disappear, and at the end we might just kind of cut it out, for aesthetic reasons. Yeah.
What kind of time synchronization do you need to do the reconstruction of the system?
Well, these were synchronized within this. This is an off-the-shelf system that you can buy from B&H Photo or someplace like that, and plug into the cameras, and you click it with a radio, and they are synchronized to, I'm going to say probably about 100th of a second.
100th of a second?
Yeah, the cameras are synchronized.
I would expect that surf changes a lot.
In 100th of a second? I don't think it changes that much in 100th of a second. I mean, it will change a little bit, right? But so you'll lose that resolution.
That wave
Right.
period is probably 10 seconds.
This wave period is probably 14 seconds.
Okay, but a quarter.
But the velocities.
The velocities
The phase speed velocity.
are meters per second. So
5 meters per second, 500 centimeters per second. So it's moved to centimeter.
Yeah.
In 100th of a second.
and that degrades the
And that's
quality.
less probably than the resolution of the image.
But also, don't forget the shutter is open for a quarter of a second, right? So, or
So it's
100th of a second.
blurred a little bit.
Yeah.
Yeah, I have another question.
Yeah.
You are showing mostly the road construction, but you've shown a couple of pictures of underwater reconstruction as well. But these were side projects and where you were not interested in quantitative reconstruction, right?
Yes and no. One of the projects that I showed was this underwater shipwreck that the archaeologists were interested in. that was a side project where I just kind of, they sent me the pictures and I threw them into PhotoScan and I reconstructed.
Yeah.
But if we had put scale bars in the picture,
My question
yeah.
is about, are you taking refraction into account?
well, so there is no refraction in the underwater pictures because they were taken underwater, and so it's all.
No. I'm
But
talking
when-
about the air interface.
Yeah.
Water.
Yeah, so that one, so the short answer is, are we worried about refraction? Yes. Are we taking it into account? No. Except that we're arguing that on kind of two angles. One, there isn't that big a change due to refraction because we've got 50 meters, the drone's 50 meters above the water, and then the water's only 3 meters deep. So there's a big, there's not that much of a displacement of the point.
It's skewed.
Skewed one way.
From the air.
Right.
Oh, okay.
Right.
I thought that, I was asking about like purely underwater.
Oh, well, the purely underwater, there is no refraction issue.
No, there is.
There is.
No one. Yeah. There is no. If you would like to discuss it.
Wait, I'm a little confused, but in the one where we're looking at the shallow water, our arguments are twofold. There is refraction, but we're also looking at it from 6 points. So we're probably averaging out the errors of the refraction to some extent. Maybe not all the way, and it might be biased, but yeah. Yeah.
Have you removed control points out of a solution and sort of gotten a sense of which ones are like most critical, like what the best strategy is for how you distribute your control points through it?
Yes, I mean but not in an organized way. And the main reason we haven't done it in an organized way is first of all, other people have done that, and so we have some reliance. But the other thing is they're too expensive for us to throw away in terms of time and energy to put them out there. So we've only had a couple of experiments where we've had way more than enough so that we could try what you're, take some away and do that. In terms of where we put them, we try not to require too many photos to be unsupported by them. So we try and get them no more than like 5 photos apart, which ends up being a couple hundred meters in our case. And we then distribute them around the edges of our area and along the topography. So we get them as low on the beach as we can and as high on the dune as we can, and places in between. So we're sampling vertically and horizontally and trying to capture it.
Does PhotoScan allow you to calibrate the cameras in advance?
Yes. Yeah. If you wanted to give it a camera calibration, you could.
So you might be able to do a sort of a sensitivity analysis where you figure out which things are most critical to have that would allow you to significantly reduce the number of control points and not have them so close together and not go through all of that effort. Maybe a modicum of a calibration is enough.
Right, and there are definitely so the couple of things. There's some rules about how to take the pictures. You might know them, but if you're going to try this at home and you want to improve your pictures, take everything from about the same distance in one collection of pictures. So about the same distance. Do not change your focal length. So don't zoom your camera. If it's a zoomable camera, don't change that. If it's a handheld, turn off the anti-shake because basically that moves the location of the image with respect to the lens, so you got to turn that off. If you've got a nice SLR, turn off the lens cleaning thing, which basically bangs the whole CCD to try and knock dust off it, and maybe doesn't come back with the exact same alignment every time. You want to shoot with a high enough speed to, the old thing of f-stop and ISO and aperture shutter speed and ISO. You want your ISO nice and low so that you've got a good, crisp, sharp picture, but you also want enough light to expose it properly, but you want a fast shutter speed, and you want an f-stop that allows you a certain amount of depth of field, which ideally is infinity and beyond, and a few other rules. But the most important thing for the PhotoScan or for any other photogrammetric thing is to get the right amount of overlap and to turn the camera plane. So not all of your images are like the worst day of our mapping on Sandwich, one of the drones, the software had the drone camera. If this is the camera plane, it would go up here, go across on a line, and then back down the line like that, and then go like that and like that. And most of our other pictures were taken, the drone would go here, then it would turn, then it would turn, and it would turn, and the camera plane was rotating, and the overlapping things were from two different angles of the camera plane. So basically, we were sampling all the different parts that the lens was seeing with a nice sample. But if you get them all skewed into one kind of bin, you have that problem with oblique where you've got water here, so you're not using the whole image. That seems to be the most important part, is to get lots of different angles of the camera plane. More than you wanted to know.
Can you, like, how much computing power do you need? I mean, you're talking, like...
How much time do you have?
You do this on your iPad? You'll take pictures of your iPad, and you process it on that, your phone?
You
Or
can.
do you need something a little bit more powerful?
There's stuff that will do it on your phone. There are apps you can download, and you can do it on your phone. Your iPad is better. What I've done all of this stuff with is kind of a low-end desktop, because I haven't upgraded my desktop. So I've got a desktop. It's got about 96 gigabytes of RAM, 12 processors, and...
Just a low end. Something you find on the weekends around here.
My teenage daughter built a better computer for $1,200. So we're buying a new one. We're buying a new one, and the other thing is the graphics card, or graphics cards, right? So a lot of the thing gets tossed over to a GPU by this.
Is the GPU process?
Yeah.
Oh, how
Yeah.
cool.
So I've never used anything that when I do this on this medium, and is that better? 96 gigabytes of RAM. I've only used about 48 total in a big project. I use all the CPUs full speed. I turn it on, and all 12 CPUs are maxed out, and the thing's water cooled, and it sits there and it goes like that for 18 hours, right? So even my models don't tend to do it that much. They have to write output every once in a while. This thing just, right? So it's very computer intensive. All right, people have to go drink beer.
Are you going to stay around?